Swayam Prabha. Digital India. Educated India.
So what we have shown is that we started with a span of these vector fields, which was some distribution. We said that it's involutive. By involutivity we were able to show that in the first step that you can transform it to some new vector fields which commute, that is their Lie brackets are 0, the new set of vector fields have 0 Lie brackets. Then you are able to show that the original vector fields can be transformed by a state coordinate transformation to E1 to Ek, and finally that you can get annihilator vector fields Hj in the original coordinates. In the new coordinates anyway you have the Gjs, but you can get the Hjs in the original coordinates also, which are basically the annihilators, right, and these are exactly going to be the addition, the Hjs are going to be the additional coordinates that we, after relative degree r, we have to construct some n minus r coordinates. These are exactly those. Okay. So what are we left with? The converse. I said that involutivity and complete integrability are equivalent. So we are left with just proving the converse. Okay, and that is what is this guy. Okay, all this does is proves the opposite side of things. Yeah. Anyway, so we don't have to look at this, but the converse proof is pretty straightforward. Once you have complete integrability, proving invertibility is not difficult, because complete integrability not just tells you the existence of these h functions, it also gives you that these dh corresponding to these h functions are linearly independent. Okay, so you have enough to claim involutivity in fact. Alright. So what is where we wanted to focus was what is the implication on feedback linearization. Okay. If you remember, we started with a system like this, yeah, single input system, yeah. So we had only an f and a g. Alright. Now suppose I claim that this distribution, which I have constructed in a rather interesting way, that is its span of g, add f g all the way to add f k minus 1 g, okay, is non-singular and involutive. Okay. Suppose this happens, okay, I mean we will see why or why we have constructed it like this, but these are my f1 to fk. I do not need actually separate f1 to fk, this is my f1, f2 all the way to fk. Okay. I am just constructing it out of the ingredients I have here. Right. Suppose this happens, I know by Frobenius theorem that delta is now an integrable distribution. Alright. What does that mean? It means the existence of these h functions, right. How many? N minus k, exactly n minus k, and with what condition? That this happens. I just wrote f1 to fk, this is just f1 to fk, add f0g, add f1g all the way to add f k minus 1g, yeah, that is f1 to fk, yeah, and hj is all of these. Okay. Does this condition look similar? It's same, like lemma 0.1, 0.2, this is the kind of stuff we had. Okay. What is this? I am expanding this, let me expand this thing now. I am expanding not just this one but all of them. Because there are many, how many are there? How many conditions are? N times k conditions, right? This is because there is k here and n minus, sorry, let us see, n minus k times k conditions, right? I believe this is n minus k times k conditions, right, because there are that many. I am going to expand them. How? In this way. Okay. Because I am just writing the Lie brackets, I am not doing anything, I am just writing the Lie brackets itself. This is del h1 del x, del h2 del x all the way del h n minus k del x. What is the dimension of this guy? n minus k rows and n columns. Yes, because each of them is a row vector, each is a row vector, each is a row vector, and multiplied by this vector field. That is, I write all of them, add f 0g, add f 1g, all the way to add f k minus 1g. What is the dimension of this? N cross k. Why? Because this is a vector field, n dimensional, and there are k such elements. So, n cross k. What is the product? What is the dimension of the product? N minus k cross k, right? That's as many conditions that I have, right? So, what I have done, I have taken this one small condition and written it in this matrix form. Do you remember this matrix? We had, no? We had, right? In 0.1, 0.2 lemma, this is the sort of matrix we have been looking at, right? Very familiar to us, okay? So, again, different looking, right? But very similar. I mean, just this thing inside has dh1, dh2 and all that, right? Other than that, this guy is exactly the same. R is just replaced by k, all right? Otherwise, exactly the same. What am I showing now? There I used it for a different purpose, but you see I am going back and forth to the same sort of expressions. That is the important thing to remember. Alright, great. But now integrability further tells me something, that these guys are linearly independent, right? That is the meaning of complete integrability, and Frobenius theorem gave me complete integrability for free by involutivity. Okay, excellent. So, what does it mean? dh1, dh2 all the way to dhn minus k are linearly independent. What does it mean? This thing has to be rank n minus k. Yeah, because each row is linearly independent, right? So, of course, this entire matrix cannot have rank more than n minus k. This is rank n minus k. Okay. So, obviously, what do we have now? This guy is of course 0. Okay, no problem. So, what we are now saying is that these h1 to hn minus k become my new coordinates. So, relative degree is actually not n minus k, relative degree is k, right, not n minus k. N minus k are these additional coordinates that we construct, in which the control will not appear, right. Obviously, control will not appear, because if I take derivative of h1 of any hi for that matter, wait a second, yeah, hi dot, I get LF hi plus LG hi u, yeah, so 0, okay. So, there is no control in this, okay, and so on and so forth. Yeah, you basically get these new additional coordinates like I told you, right. These h are what become your additional coordinates when you are looking at partial feedback linearization, okay. Now, I do not have anything here, I have something else there, but what does, I mean, it's nice to also wonder, what does involutivity of this vector field mean, of this delta mean, okay. What does the involutivity of these guys mean, okay. Involutivity means that if I take Lie bracket between any two of these, any two, then that has to be in the span, okay. So, suppose I actually try to look at that, okay, try to see if it really happens, right. So, if I take say Lie bracket of G and add f G, what is this? Is this anything that we know? So, what is add f G, by the way? Add f G is, yeah, add basically gives the successive Lie brackets, right, okay. So, what does this give me? What do you think happens here? So, we have to do the entire computation, right, we have to do a little bit of the computation. This is a little bit complicated, yeah. Let us see if we can, let us give it a shot, yeah? Even I have not tried it. So, this is d add f G G minus dg add f G, yeah, okay. Let us see, does this help us in some way? Can I simplify this further, or this is it? Apparently not. Yeah, yeah. So I was thinking we'll be able to simplify this further, but no, doesn't look like I can simplify this further. Okay, so I'm just going to make that remark. Cannot I was thinking if there is some nice expression or simpler expression that will come out of it. Doesn't look like it, not on the face of it, unless one of you can work it out and tell me. But I don't think it's turning out to be any further simpler. Yeah. What this condition is that this is essentially the relative degree condition. See, what you were doing is, what we were doing is we were basically taking the output, a particular output. Alright. Remember, the entire feedback generation that we were doing until now was relying completely on a particular output. Okay. What if you don't know what is that output? How do you verify if you have any relative degree and feedback generation and things like that? Yeah. Then you have to use this kind of a method, where now you notice this is not dependent on any output, this condition. So what you have to do is, you have to, if you have a single input system here like this, and you have no idea what output you can choose that will give you some feedback generation, because otherwise you can do bunch of trials and errors, right? You will have to check these vector fields or this distribution. Yeah. And what will you have to do? You have to verify that this distribution is non-singular, which means what? That each of these are linearly independent for all arguments p. At every point they give you linear independent vectors. Okay, that is what it means for this to be non-singular. Okay, and involutive, you will have to actually check that they are involutive. Okay, unfortunately it is not obvious that it is still giving you any output. Yeah, at the end of this exercise, if you see, it's not very easily evident what is the output that you can use. Okay, but when we are doing the full state feedback generation, you will see that it becomes very easy to find the output using this method also. So basically this gives you a method of sort of finding that output that will give you a feedback linearized system. Yeah, here not so much. I'll also have to see how to get the output here. One thing that's sort of evident here is that these coordinates that I got, right, if I keep taking successive derivatives, alright, so I take the first derivative, I get no control, alright, no problem. I take a second derivative, I will get what? LF square HI, right, I will get an LF square HI, no control again, right. But similarly, if I take k minus 1th derivative, I will get LF k minus 1 HI, right, and still no control. Okay, until this point here. Yeah, when I take the kth derivative, right, so this is basically add f0 in 1. So yeah, in the kth derivative of hi, I will get add f k minus 1 g hi. Yes, this is also, I believe, 0, right? Correct, because right, by this guy is also 0, right. But if I take hi k plus 1, okay, then the control will show up. Okay, but that is still vague. Yeah, it's not evident that that is a good choice or not. Okay, so I'm just commenting on the fact that this HIs themselves could also lead to feedback linearization. Yeah, the output that will give you feedback linearization. Okay, not just as the extra states. Okay, one way to look at them is that they are the extra states, right, but they could also lead you to the output that will give you feedback linearization. Okay, so it's not very evident here because you need additional conditions. You need to know that L add f k g hi is actually non-zero. That condition is not being posed anywhere here. Yeah, you need that the higher derivatives actually have non-zero input. So that does that happen or not is not very clear in this case. Okay, so anyway, so this is the implication of Frobenius theorem in partial feedback linearization? Basically, it comes into play when you don't have an output which you can keep taking derivatives of and try to find the control. Yeah, you may not have a suitable output. In those cases, you can actually directly use the vector fields of the system itself and the Frobenius theorem to see what is the relative degree of the system. It is not very obvious in the case of partial linearization that how to find this output. Okay, this will give you the relative degree, but how to find the output is still a little bit of a jugglery at this stage. Okay, now if you go to the full state linearization, then something more can be done. Okay, that's what we want to look at now. All right. So we are again back to the notion of integrable distributions. Don't worry about it. This is a repetition. I already told you that if you have a distribution which is a span of some vector fields, right, then if you think of annihilator theory, you are looking at some y's which are annihilating each of these. Yeah, that's essentially what we have the DH for. Okay, so that's what it's mentioned here in just a different notation. Please don't worry about it again. You say that the distribution is completely integrable if it is annihilated by these n minus r lambdas. Okay, this is just different notation. Yeah, going from h to lambda. Yeah, of course you also know what is involutivity. I am not going to actually stress on it again. So we want to look at now the conditions under which you can completely feedback linearize. Okay, we have already looked at the condition, by the way. There is nothing very big about it. We have already looked at partial feedback linearization. So when k becomes when this k becomes n, you have complete feedback linearization. All right, that's it, right? Because we have already looked at the case when for arbitrary k. So if k becomes n, it is completely feedback linearizable, and that's what we are writing here. Yeah, this is again for this particular system. X dot is okay, doesn't mention here, but this is again for the system assumed is still x dot is f of x plus for this system. Actually, I apologize, this should be this section. For this section, this is the case. Yeah, all right. So what have we done? We are talking about some necessary and sufficient conditions, right? And we are constructing this matrix. Okay, G, add of G, add of n minus 2, add of n minus 1. Okay, we want this to be rank n. What is this matrix? Same thing that we constructed, right? Just taking k equal to n, right? Same deal. What, because what does it do? If all these are linearly independent, then you get a non-singular, a non-singular distribution. All right. So what, that's the first requirement, that this has rank n. Yeah, he is talking about a particular point x0. Okay, but typically you will want it for all x0. Okay, all right. Okay, great. So this is rank n is the same condition that we saw before, because this is what gives you the distribution delta. Okay, right. Next, now we are looking at the distribution here. Well, fine, in this particular case the one of them is removed from the distribution. Okay, in this particular case the distribution is removing one term. Okay, this is for a particular reason, for a very specific reason. We will look at it subsequently. All right. So the distribution is not spanned by G add of G all the way to add of n minus 1 G, but we are going only until add of n minus 2 G. Okay. All right. So we are asking for the distribution to be involutive, just like before. Okay. So same conditions, we are creating a distribution based on the vector fields in the system, which is f and g, right? Using the f and g, we have constructed this distribution, and we want it to be non-singular and involutive. All right, and Yeah, that's it. We want it to be non-singular involutive, and of course we've also said that for non-singularity we have sort of added this additional term here. Okay, we have added this additional term here. All right. Here the h function or the lambda function is used in a slightly different way. Okay, that's what I want to highlight now. I hope this is clear. Do you see the identity between this and what we did in the partial linearization? Are you completely lost? You see what we are doing here? At least I hope you can see that these expressions are very similar. Okay. Otherwise we are just trying to apply the Frobenius theorem, which is saying that if your distribution is involutive, it is completely integrable, and complete integrability means I get these functions h. Okay. And I want to do something with those functions h. Okay. We don't know what we want to use them as, but we want to use those functions h because they have some, these nice properties, which is basically something like this annihilator type properties. Okay. So that's really the whole plan. All right. So let's see. Even if we forget what we have looked at earlier, let's look at this in a separate context. So we have taken these vector fields. Okay. And again we will also try to look at some examples, of course. And we are saying that these vector fields are independent and therefore rank n, and further now we construct a distribution out of all of them but one. So the last one I have removed. Okay. So now this has only n minus 1 vector fields. So what will be the dimension of this distribution? What would be the dimension of this distribution if it's a non-singular distribution? Because I already said G, add f G, these are all linearly independent. Yeah. So what would be the dimension of this distribution? How many vectors does it have? N minus 1. Okay. And what is the size of each vector? N. So this is an n by n minus 1. If you look at it in matrix form, it's n by n minus 1. Right. So what is the rank of this distribution then? N minus 1, cannot be more than that. Yeah, n is larger anyway. Okay. So the idea is that rank of D is n minus 1. This is why I have the non-singularity. Okay. I have already assumed involutivity. Okay. So I can immediately invoke the Frobenius theorem and say that it is this distribution is now completely integrable because it is non-singular and involutive. Okay.